Because in like the homework you talk about like submitting like a link to a repository, but if it's a private repository, I don't think that works with GitHub. I think you need to like go to like accounts and ask them to be like a collaborator or something.
Yeah, there's some instruction to share with that. If you cannot find it, I will look into it. Okay, because until very recently, the GitHub allows you to do the private, and you can share it with some collaborator. And here, collaborators are referred to our TMs and TA.
Because in the homework, all it says is, please leave the link to your repository in the homework submission.
Yeah, I mean, if your private link cannot be accepted, there should be some like a private link to somebody else who wants to look at your code. But if you cannot, we'll take a look at it. Okay, and or we can share with you the email account of our TMs, and you can edit them as a collaborator in your private project, so that they can feel free to access your code. Okay. Any other question? Okay, so the last point I want to emphasize that. Such kind of homework assignments are not feasible to be rushed on the last minute, because you have debug code. Right? When you debug the code, it is highly unlikely that you can spend 20 minutes to make it work. So that's why I suggest you to start early. Right? And you can implement it, and feel free to find out all kinds of bugs and tune it on the data to get reasonable results. Otherwise, like if the deadline is in 3 hours, honestly it's not possible. And also take advantage of the office hours, because recently I found that office hours are always empty, right? And according to my previous experience, like the office hours was filled with students always like 1 day before the deadline. But that won't work for practical assignments. Okay. So now that we have discussed our first practical machine learning algorithm and a model like decision trees, it's time for us to look at some more general ideas, more abstract concepts to investigate the supervised learning task. So today our focus will be a few fundamental concepts in computational learning theory. This is a very brief introduction. It might be boring, but again, we need some kind of stuff, some mathematical framework to rigorously quantify or describe this topic, rather than just list you a bunch of different types of models and we do not know why it works and when it works, right? So actually, as we say, those concepts and the basic results are the main motivation for highly successful and popular machine learning models like support vector machines. And to explain why support vector machines work, how it is invented, you must know those kind of things. Okay, so we're gonna first introduce a few key concepts in the general framework for computational learning theory. What is the empirical error and what is the generalization error? What is the goal for computational learning theory? So basically, one important goal in computational learning theory is that can I estimate or give some like upper bound of your generalization error according to your empirical error? This is a very interesting problem. And then we're going to define a very important concept called pack learnability. So that's a brief for probably approximately correct learnability. It's kind of tedious definition. It's weird, but as we'll see later, right, it's actually a very natural definition. And then we'll make formal connections to the principle of Occam's reasoning. So we briefly mentioned what is Occam's razor's principle before, right? We said, okay, we are guided by the Occam's razor to construct decision tree to be as small as possible, right? We just said, okay, intuitively, seems like to find out the smallest tree that can summarize data is the optimal choice, right? But why? Right? How can we justify it in a more rigorous way rather than just intuitive, right? So we're going to use the concepts we introduced in the computational learning theory and to give some justification. Okay, so before we introduce the concept, right, let us first step back, right, look at the general framework of supervised learning. So this is our checkpoint, right, the bigger picture for supervised learning. Right? So we mentioned that before, when we conduct supervised learning, we need to be clear about three important ingredients, right? First, what are the instances? Right? All the instances consist of the instance space, namely, what are the instances we want to build a classifier to predict, right? And also labels, right? Label space. If your label space are only having like 2 labels, you're doing binary classification. Multiple labels, you have a multi-class classification. If it is continuous labels, that means your label space contains like infinite, uncountable number of labels. It's called regression, right? And then hypothesis, right? So what does hypothesis mean? This is associated with the specific learning algorithm or model we use, right? As we mentioned, that what is learning algorithm? Learning procedure, machine learning procedure is essentially a searching procedure. Right? Once you have identified the instance space, the label space, we always assume that, okay, there's some kind of target mapping or ground truth mapping from the instance to the labels, right? And our goal is trying to find out an enough good function which is close to the target function. In the ideal case, we want to directly identify the target function, right? But in most practical cases, it won't work. So now that the learning is a searching procedure, a natural question would be like, what kind of range, what range of the functions you're gonna search for that? This is called hypothesis space. So hypothesis just means one particular function you search, right? And then to run our learning algorithm, we should prepare a set of label data, right? So the label data are pairs of the instances and their labels generated by the target function. Then we feed those label data to our machine learning model and algorithm, like decision tree, ID theory, whatever, right? And then through running a decision tree or other learning algorithms, it will produce a particular hypothesis, which sometimes we also call like model-specific model, right? That's our learn model or some prediction function. We denote it by small h. This is our learn model or our learn hypothesis. And then we're going to use this learn hypothesis h to make prediction for wild examples. So this is the protocol to conduct supervised learning, right? Mm-hmm.
So in the case of the decision tree we talked about, like first ever decision trees, label data would be like the shapes with the labels like color and shape. Like
you mean that shape classification task, right?
So the label data that we would be building a model, we would be applying the function to build a model. Label data would just be the shapes and their attributes.
Yeah, the instances are just a set of attributes that describe each specific shape, right? The attributes consist of the shape and the color, right? And the label would be like A, B, and C, right? We have 3 labels, right? So, and regarding the learning algorithm, we have many specific learners, right? Decision trees are the first concrete one we have discussed, right? And later we'll talk about perceptron, the ancestor of artificial neural nets, least mean square method, support vector machines, and logistic regression, and etc. a lot. Right? So these are the whole framework of supervised learning. I hope that will just will reinforce your idea about that.
So it's like the hypothesis, for the example, like the sunny and overcast and all that stuff. Is that like whether or not you go play tennis? Is that what your hypothesis is, or you give an example of hypothesis?
Hypothesis is just some kind of classifier. Here we just define a function, right? So the input of function is just all the attributes and features that represent the instance. The output is just the label, right? So I can construct a random hypothesis like no matter what kind of features, the inputs of function is, I just report the label randomly. This is one hypothesis. Of course, it's a bad hypothesis, right? Another one is like another example could be like a constant hypothesis, right? No matter what kind of input features are, just report, okay, I'm gonna stay in my home. It's not a hypothesis. Obviously, it's not as good as one, right? And then you need to specify for any learning algorithm a range of hypotheses, which we call hypothesis space. Then your learning algorithm is going to search over the whole hypothesis space to find the one which we believe is closest to the true function or target function, right? And how do we conduct the search? The search actually are guided by the label data. Does it make sense?
So you're saying that, like, in relation to the data we've been using, like, you're saying we suspect that there's like some true relationship, like, given this data we can predict whether someone's going to play tennis always. And our hypothesis is like the actual decision tree model that we generate.
Yes.
And we're trying to find the model that's closest to like the true relationship.
Yes, exactly. Any other? Yeah, I'm happy to hear that you guys are trying to relate those more abstractive framework to our detailed learning algorithm.
Sorry, well, last thing, and the label data would be comparable to the table that we built the tree off of, like is it humid, is it not humid? That's the label data that we're using. We're feeding the function to build our hypothesis.
Yeah.
Yeah.
Those are features, right? So remember, when we introduced the supervised learning, we had to convert the original instances into a feature vector representation. In our play tennis supervised learning task, those feature representations consist of like 3 or 4 binary features. So it's like 4-dimensional binary vectors. Right? So then if we construct such kind of mapping, then your input features, your input of your prediction function will be these 4 binary features. Right? The output will be just the binary label, whether you play or not. Right? Or probably it's not binary features. Some features can take 3 values. Any other question? Okay, so in addition to this general framework, we also talk about other ideas, right? So feature representation, right? I just mentioned, right? So we mentioned that this is a very important pre-processing step. You're gonna use a set of, you're gonna extract a set of numerical values to represent the original instance. Like if I want to do the face recognition, I cannot directly throw a picture to a computer and ask the computer to give you the label on that, right? Whether it contains cat or not. Right? You have to first use a set of numerical values to represent this image. This process is called feature extraction. It's a very important pre-processing step. Right? You will see the importance when you do your course project. Right? And also we talk about overfitting. So I will give you some empirical example of overfitting. Right? Overfitting basically means that, intuitively means that, okay, you fit the training data so perfect, right, such that when you predict the future test examples, your performance drops. That's not good. We give an explanation why overfitting is not good. It's because in real-world applications, your training data are always mixed with some noises. Right? So if your learning algorithm tends to perfectly fit every training example, it will perfectly fit all the noises inside the training data as well. Right? And those noises, unfortunately, usually will mislead your learning procedure and end up with a bad hypothesis, which gives a bad prediction performance on the future examples. Right? So we use some kind of one toy example to illustrate the issue of OP. So those are all we have discussed up to now, right, regarding the general framework for supervised learning. So now, let us talk about setting of computational learning theory. So, in this framework, we assume that we have a learned model, namely some stress-rate hypotheses, which are trained on some fixed training set, and then we deploy it in the wild. Right? We want to apply it in practice, and that means, okay, I might have to predict all kinds of future examples that you have never seen in the training. So a natural question, also this very important question, is how well will your learned model perform on those future examples? Right? So now, if we do not use computational learning theory to answer this question, how will you address this question? How will you answer this question?
It depends on how well we train the model.
Yeah, of course.
I mean, the number of examples that we provided.
Yeah, that's actually something the computational learning theory cares most. Like, it wants to relate the number of training examples you use during the training to the performance in testing future examples. Right? But right now, let us forget about it right now. Right? I don't know any theory, right? And now I have a model which has already been trained in hand. Right? I want to answer or estimate what is the future prediction performance of our learned model. Right? How will we do that?
You probably have a set of data that you didn't train the algorithm with, and you would teach the algorithm and then compare, see the percent accuracy of predictions, and then like assume that would be generally proportional to the real world, or like unlabeled data that you're trying to.
Yeah, exactly, right. You have a same, yeah. That's very natural, right? This is actually what we're doing right now. Every time, even you have some theoretical characterism or claim on that. In practice, we're still like collect a bunch of test examples, and the more test examples you have, the more accurate your estimation for the generalization performance of your trained model, right? So this is the practical principle, right? But now, our goal in the computational learning theory is that, okay, I do not want to do this. I just want to give some theoretical argument or claim about my learned model's generalization performance. How can we do that? That's one. Not only, but one of the most important questions the computational learning theory wants to address. So we need to introduce a few basic concepts and notations before we discuss about this, right? So first, in a supervised learning setup, we'll use X to denote the instance space, namely set of all possible instances, right? And then we'll introduce the notation for concept space. So we'll use C to represent concept space. So what does concept space mean? Concept space just means the type or the family of the target function. So like, if you believe your target function is just a linear function, then your concept class is just a set of all possible linear functions.
Is C different from hypothesis space?
What?
Hypothesis space.
It's different from hypothesis space.
Is it? Oh, different.
C is different. C is not hypothesis. C is called concept space.
So is it a subset of hypothesis space?
What?
Is it a subset of hypothesis space?
No, it's not necessary. Actually, in many cases, there's no guarantee that your concepts class will be contained in a hypothesis space. Actually, they might overlap. They might just overlap. Okay, but just be aware, concept space just means, okay, which family of the functions that your target function belongs to, right? So the concept class also relates to the supervised learning problem itself. Suppose I know my instance space are just the binary, like n-dimensional binary feature vectors, right? Your label space are binary. Then you know that your target function must be some binary, a Boolean function, mapping from binary input vectors to binary output. Then you can also say, okay, my concept space are just the Boolean functions. But in summary, a concept space just means, okay, what is particular type of your target function? And as you just mentioned, right, in the following, you will introduce hypothesis space. This is different from concept space. So what is hypothesis space? This is something determined by a learning algorithm, namely the set of all possible hypotheses from which the learning algorithm is going to search and identify one which you think is best to approximate the target function. So of course, different for the exact same supervised learning task, the concept space is always there, right? It's fixed. It's known, right? But the hypothesis space could change according to the specific learning algorithm you use. So suppose my hypothesis, my concept space is just linear functions. I know, okay, this target function is just a linear function of those input features. But when I train my train my machine learning model, right, if I use linear models, okay, my hypothesis space is also a set of linear functions which are same as concept space, right? But I can also use nonlinear functions, like quadratic functions. Then my hypothesis consists of all possible quadratic functions. So say now hypothesis space does not overlap with the concept space. This is some kind of choice by the machine learning algorithm. And then training instances, right? Training instances, here we always consider binary classification cases. That means your label is either +1 or -1, right? So the training instances are a list of pairs where each pair is a specific instance and the label of that instance. So the label of that instance is actually the function value of the instance, right? The target function's value, f of x1 and x2 to f of xn. Right? So what is the learning procedure? What do we expect? What outcome does we expect for our learning procedure? Right? We want that, okay, when we find out hypothesis, which from our hypothesis space, then for any input space x, for any input instance from instance space, the prediction made by this learned hypothesis is the same as prediction made by the target function. Namely, h of x is equal to f of x, right? So now, we already have like two cases, right? Need to take into account. So first, suppose my learning algorithm can reach these results. Namely, I can find out hypothesis such that for every instance in the training set S, h of x equals f of x. So what does that mean?
Unlike your model predicts all the values that you see in like your labels.
Yes. That means, okay, you have something to say? Okay. So that means your training error is 0, right? You perfectly fit the training data. So such kind of learning algorithm, we call it consistent learning, means that, okay, I can consistently predict all the training examples.
Then does not lead to overfitting.
Yeah, of course it leads to overfitting. If your training set S are corrupted by some noises, then your consistent learner will suffer from overfitting.
So why are you using like the first one using like the subset symbol and then the next one using the element symbol? What's the difference there?
Where's subset symbol?
It may be a resolution.
Is that
problem.
resolution? Because
Here?
like one is like it's like the
Oh,
It's very dim, but it's there.
let me take a look. Oh, I think it's a project issue. It's not subset symbol. It belongs to. There's
okay.
one small dash here. Oh, I'm sorry for this. I don't know why it looks like this. In my slides, it is explicitly, belongs to. And the two symbols are exactly the same. Okay, that's funny. Right, yeah. But X is some element inside S. It shouldn't be belong. It shouldn't be contained. It's not subset. It belongs to. Okay. So this is the first case. And the second case will be like even more ideal. Second case that, okay, after I got my hypothesis H, right, I can ensure that for every element in the entire instance space, H of X equals X. That's the most ideal case, right? That means, okay, I exactly find out the target function F. For every prediction, the prediction for every example in the instance space is the same as prediction of the target function. That basically means H and F are the same, at least on the instance space.
So is the instance space just the set of examples that you have like information for, or is it just every example of like?
It consists of every examples which are possible to be used for prediction. It's not all the examples is possible to be used for training. It's not. Like my task is to do the image classification, right? So what I can collect 1 million pictures for my training set, but those are far from the instance space. Your instance space should be like all possible pictures in this world, right? But you can only pick up a small portion of them for the training. Okay.
What does the S times -1 and 1 mean? Yeah.
This one?
Yeah.
So this is have you taken the discrete class, discrete mathematics before? Okay. So it's called Cartesian product. It just means, okay, I have a set in S, a set of elements in S, right? So I have another set, right? So just enumerate all possible pairs of each element in S, each element in this set. So it basically says, okay, what is all possible combinations of every element in one set and the other element in the other set.
So the f of x is equal to -1 over 1.
Yes. Okay. But this is just tell you like what does the training instances look like. So it's pairs of the one element in S, the other element in this set, right? Of course, whether it is -1, +1 is determined by the target function.
So that's for the binary classifier where it can either be like true or false or -1 or 1.
Yeah, of course.
So if it was like maybe if it had like 3, it would be like a different Cartesian product there.
Yeah.
Okay.
Like if you're doing like if you define that your negative label will be 10 and the positive label will be 20, there's another, of course, another set of symbols, right? But they essentially represent the same thing. If you have a multiple class, right? So 1, 2, 3, 4, 5, then the label will be 1, 2, 3, 4, 5, whatever. Any other question regarding the definition of notations? This is very good because we need to be clear about those notations before we talk about the definition based on those notations. Okay. So another important assumption in our theory framework is that we assume the training instances are generated by some unknown fixed probability distribution D over the entire instance space X. Why? Because the practical world are filled with uncertainty, right? So actually, in most applications, you have no idea about how the training instances or test instances are generated. And then we're going to assume they are produced by some unknown mechanism with uncertainty. So those mechanisms are best described by probability theory, right? So we use some data distribution to represent this unknown mechanism D, right? We assume, okay, my training instances are generated by this unknown data distribution. Of course, my test instances are generated by the same distribution as well. Does it make sense? And then, in practice, as we mentioned, right, as we discussed just 2 minutes ago, right, once we obtain our learned hypothesis, right, you want to know what is the generalization performance on that, namely the prediction accuracy on future same samples. What can we do, right? The procedure is that we'll just draw a bunch of subsequent examples from this distribution and throw them into our learned hypothesis and test the accuracy, right?
So is the distribution the likelihood of like a certain instance coming up, or the probability that given an instance, the probability that the label for that instance is something?
Here's just some data distribution. Actually, you even do not know what is the probability density. You have no idea about how this distribution look like. Probably it doesn't have any analytical form. We just assume, okay, it is governed by some underlying distribution. So, like, to give a more intuitive example, right? So, if you want to look at, you want to collect the face recognition training images, right? If I want to collect that, how can we do that? We just crawl the web pages and to download all the pictures, right? Those pictures have some regular patterns. Right? It's very unlikely that you get like weird pictures. So you can imagine that they follow some kind of distributions, right? For some particular type of pictures, they have a better chance to show up. For some very rare pictures, it have a much lower chance to show up. So that's why we say, okay, it follows some kind of distribution.
So let's say you have like all the like penny stocks in the world either go up or down. The distribution is just saying that like you take a sample of that, they're probably whether they go up or down is decided by the same mechanism as the whole.
Yes.
Yeah.
Yes. Exactly. Right.
So are we only concerned with the sample distribution? Like we're not. It's not like regular statistics where we're trying to see if the sample is close to the population. We're just like the sample is all we're concerned about.
No, we actually do not concern about like what is the details about this probability distribution.
Yeah.
Yeah, we just assume that okay, it is governed by some distribution. a highly complicated distribution. It's so complicated that we can only view it as a black box. Well, if you powerful enough that you can estimate all the details of probability distribution, honestly, you don't need to conduct supervised testing. You know all the mechanism, right? Then predict one of these labels will be much easier for you. But of course, you need to be aware that the appearance of those instances follow some kind of statistical patterns, right? And which are described by some underlying distribution. All this distribution is highly complicated. This is just conceptually. That means, okay, there must be some data distribution. Although in practice, we do not care about the details of this distribution. Does it make sense? Is everyone comfortable with that? And also, after we conduct training, right, how do we evaluate the performance, right? I randomly draw another set of examples which we have never used them for training. But how do we draw that kind of examples? We essentially draw them according to this unknown data distribution. Like you randomly collect a bunch of documents from Google for training, right? You train your classifier with 10 layer neural nets, right? Now I want to test my performance. How can I perform the test? I use the same way. Right? I go to Google and just random download and search for another 1,000 documents and throw it into my classifier to get predictions, right? So the collection of those test examples follow the same data distribution. This is a basic assumption in the computational learning theory. Of course, I believe that's reasonable, right? Everybody feels comfortable with that? Okay, yeah, but of course, I mean, in theory, you can assume different assumptions. Like you can assume, okay, my training instance come from one data distribution, but my test instance come from another data distribution. It is possible, right? You can try to give some derivation and prove the theory based on the connection between the distribution of the training instances and distribution of test instances. But this is beyond scope of our class. Okay. So now let us give the most important concept definition in computational learning theory. It's called generalization error. So what is generalization error? So given a data distribution D, for examples, again, it's not necessary for us to know what is D, right? What is the explicit form of D, right? But we need to assume that we have some kind of data distribution to generate examples, right? Then the error of a hypothesis H, which is very likely the outcome of our learning algorithm, right? With respect to a target concept F is defined as the probability that you use your hypothesis to make wrong predictions under the data distribution D. So this is a definition of generalization error. This is a rigorous or formal definition of the generalization error. That basically means that under the data distribution D, from the prediction made by the true or target function. Does it make sense? Mm-hmm.
It's just for 1x?
Yeah, 1x. Just for 1x. Remember, this is a probability. It's not like I give you a specific example. You tell me it's 1 or 0, and I tell you, okay, you're correct or not. This is the probability you're making wrong predictions. Mm-hmm.
What if H is extremely close to F, but not exactly to F?
Then this error is close to 0, but it's not exactly 0.
We don't have a target function F, so how can you calculate the probability?
Yeah, that's a very good question. Actually, you cannot calculate the generalization error. But this is a concept, right? It's just the concept means that, okay, there must be some objective value which represents the generalization performance of your hypothesis, right? And in practice, what we have done are just an estimation of this generalization error, right? So like I just randomly collect 100 test examples from B, right? And then I use my H to make predictions and count how many mistakes I have made in the prediction. So say I made 9 mistakes out of like 100 predictions. So I claim that, okay, my test error is about 0.09. So that means this 0.09 is an estimation of your true error.
When you don't have access to target function, how you can say, for example, 9 of 100 is not great in our prediction?
We don't have access to F. That just means I don't know the form of F. That does not mean, okay, I don't know the label, right? So, okay, take an intuitive example. Like, we know human beings are very good at recognize faces, right? Like, I present you with one picture, I can tell you, okay, this is a cat or not, or this is me or another guy, right? So, can anyone write down a function that how human eyes and brains work to map those image pixels to the label? No one can do that, right? But can I give you the label? Yes. But the problem is that, okay, now that I cannot access the exact form of F, I cannot compute this probability, right? Because I'm gonna, if you want to compute this probability, you have to do some integration, right, over the distribution of X and the form of F. Right? But at least for a set of discrete examples, right, concrete examples, I can give you the labels for that. I can know the outcomes of that. Thus are used to give an estimation of this error, but it's not the true error, right? Because when you draw another 200 examples, you make predictions, you end up with the number of mistakes you made, and you calculate another estimation, right? Which could be a little different from 0.09. But keep in mind, right, although this in practice is not computable, right? We do not know that, but such kind of value exists. It is there. The only difference is that I cannot arrive at. Does it make sense? Okay, this is a true error, the definition of true error, right? So to give a more intuitive illustration, right? So suppose this is our instance space X, right? Consists of all possible instances, and I'll have my target function, target concept here. So we use this blue ellipsis to represent all the set of instances which are labeled as positive by our target function. So suppose I have another, I have learned a hypothesis H, say by my decision tree. Right? So I use my decision tree to label all the instances in the instance space say S, and turns out I have another set of positively labeled instances, right? So obviously, there are kind of a large overlap between the truly labeled, truly positive instances and my predicted positive instances, right? So where does the true error comes from?
So the portion of the overlap.
Yes. This two part, right? And the error comes from the part where our target function F and the learned hypothesis H disagree, right? And then you need to compute the probability that the instances appear in this disagreement region.
Do you differentiate between those different types of errors?
Yeah, because remember, the instances comes from some data distribution, right? That means this instance might have different probability to appear in it than this instance. That's why we need to calculate the probability that all those instances in those disagreement areas appear. If the data distribution is kind of uniform distribution, well, it's pretty straightforward, right? because all the mislabeled instances have the same kind of chance to appear, right? But if your instances obey some kind of highly skewed distribution, that may change a lot.
I mean, like, there's like type 1 errors and type 2 errors here, like ones we incorrectly labeled and then correctly labeled ones we missed. Like in the error function up there, are they like
No,
equal?
this is nothing. This has nothing to do with type 1 error, type 2 error. We do not differentiate the case that the true label is 1, but you predict as 0, and the true label is 0, predict as 1.
So just wrong is wrong.
Just 1. Yeah, the wrong is wrong. Yeah. Now, of course, yeah. I mean, your point is important actually. If you want to differentiate different types of mistakes, like if you predict wrong, predict negative as positive, have different costs as predicting positive as negative, then that really matters. And then you need to differentiate the case system and make separate analysis. Any other question?
So suppose if we have an instance where the two are not overlapping but very close, and then compared to the other two that are not close but still not overlapping, so the error is going to be the same.
Can you repeat it again? I didn't get one.
So for example, think of these two circles. Think if they're not overlapping at all, so the probability is 0, right? For the error, and then but they're very close in terms of distance. Versus another example where the two are far from each other, the error is going to be the same for these two cases, right?
So I mean the first case that your two ellipses or two circles are very close.
They're close but not overlapping. They don't overlap.
They don't overlap.
Yes.
But how do they collapse? How do we close? How are they close?
Disjoint is disjoint. He's saying like if their intersection is 0, does it matter how far away they are?
Yeah.
You're saying no, it doesn't matter. Disjoint, or like if they're not related, they're not related. There's not like different sizes.
Okay. So if the two circles are completely disjoint, right? So you still have like disagreed regions. The regions will be like the positive labels made by H, and also the region which contain all the positive labels made by H, right? And you're gonna like compute the probability of all the instances falls in those disagreement regions, right? But again, remember, the probability varies along with the position of the regions, because your instance X follows some distribution, right? So remember, X, when it appears here, has different chance when it appears here, in general. So that means, like, even you're completely disjoint with each other, dependent on your locations, the error will still be different. Does it make sense? Like, suppose this is your all the positive labeled regions, right? And if your hypothesis says, okay, label all the positive instances here, then how do you compute the error? The error will be, okay, this part of region are disagreement, right? You have to compute the chance that the instances appear in this part and all the instances appear in this part, right? This is one probability which represents the true error, right? But now supposedly you have another hypothesis H, which ends up predicting all the positive examples here. So if you want to compute the true error, it will still be like the probability of all the instances appearing in this region, and also all the instances appearing in this region. So remember, the probability that instances appear in this region might be very different from probability that instances appear in this region. So your errors can still be different. Only when, okay, I know that this data distribution is uniform, like every instance has the same chance to appear everywhere, then it doesn't matter. Does it make sense? Okay, great. Yeah. So, in contrast to the true error, as we just discussed, right? The true error is some kind of objective value, but we were never able to reach it, right? So we want to look at some ponderable error, which is called empirical error. So what is empirical error? So for target concept F, the empirical error of a hypothesis H is defined for the training set S as the fraction of the examples X in S for which the functions F and the hypothesis H disagree. Namely, H of X is different from Fx, denoted by error SH. So it's a kind of tedious definition, but it's basically it's training error. This is called empirical error. So basically means that, okay, how many training instances your learned hypothesis is going to misclassify? I mean the fraction of your misclassified training examples by your hypothesis. This is called empirical error. But oftentimes we also call it like training error, right? So you can see the training error is actually determined by the specific training set, right? So different set of training examples will end up with different training error. So that's why we index this by the training set S. So now, with the definition of the training error and true error, we can give a more formal definition of overfitting. Right? So here's the definition. So when we can claim that your learning model suffers from overfitting, that is, with the empirical error on the training set is substantially lower than the true error. That means, okay, you're doing very well in training set, but your generalization performance predicting the future unknown examples really suck. So that's the definition of overfitting.
The larger your training data is, the less the overfitting affects it. Is that true?
Yeah, that's intuitive. But if you want to explain it, if you want to justify it, there's some kind of a theory can help you justify it. But yeah, generally speaking, your argument is true. So you can imagine that, suppose I have in the extreme case, like suppose I am able to collect all the instances in the instance space as a training set. Then your training error or the empirical error is exactly the same as the true error, right? So now we have all the notations necessary for us to introduce all the concepts, right? To summarize, right? So in the general case, we have a big X to represent the instance space, or Y to represent the output space, right? And D is the unknown distribution over the instance X to prepare the training data and test it. And F is an unknown target function which maps the instance space to the output space taken from a concept class C. Right? So remember, the target function is an element in the concept class. Right? And the hypothesis, right? Hypothesis is some function, also a function which maps from instance space to the output space. And this function is selected by our learning algorithm from a hypothesis space H. And also, how to guide our learning algorithm to select hypothesis, right? So we're going to use a set of training examples S, and suppose in this big S, the training examples, we have M training examples where each training examples are joined from the data distribution D. And the label of this training example is made by this target function. And then we have two metrics about the error of your learned hypothesis, right? True error is denoted by error D because it's determined by the data distribution, right? And also the empirical error is determined by the training set. So this is a list of our notations. So now I want to answer a few theoretical questions. Right? So the first, probably the foremost question in computational learning theory is that, can we describe, characterize, or bound the true error given the empirical error? This is actually the core problem in computational learning theory. So as we know, the true error is not reachable. We do not know that. We know, okay, it is there, we'll never be able to do that, to find it, right? And then the question, like, okay, it's very easy for me to know my empirical errors. When I conduct my training, I can use my training examples to calculate the training error, right? So then can we invent a reliable method to claim how does the generalization error relate to the empirical error or the training error? A second question would be like, is the concept class C learnable? Basically means that, okay, is this particular type of target function feasible to learn, right? So to answer this question, we need to know what does it mean for learnable, right? So does it mean, okay, it's too costly to learn it, or it's too complicated to learn? And how many examples does a learning algorithm need to guarantee some good performance? So this problem is called sample complexity. I also know how do we characterize the good performance. That's another interesting definition. It's different from our intuition, actually. And how much cost does an algorithm take to learn a special type of target function? This is regarding the computation complexity. Well, I believe everybody is sensitive to this, right? When you run any algorithms, you need to care about how efficient your algorithm is. And when you conduct the supervised learning, don't be too optimistic. You should be prepared. First, in most cases, we cannot expect our machine learning algorithm can learn a concept exactly. Because in many cases, you even do not know which concept class your target function belongs to. And because of the limited size of your training data, because the training data are always a finite set of examples, there are labels, right? There will be generally multiple concepts or multiple hypotheses. Each of them are consistent with available data. Meaning that I might have like 10 classifiers. Each classifier can perfectly fit the training data, the training error of 0. Then which one would be the best one? Which one could be the target class, target function? I do not know, actually. And unseen examples could potentially have any label. Why? Because we do not know the distribution of the data. The distribution D, which generates data. This distribution can be highly complicated. Right? You'll never be able to know what does the next test example look like. Right? It is very different. If it is very different from all the training examples, then it might have like very different prediction as compared with your learning classifier. And sometimes you have to like be realistic. So we agree to misclassify some uncommon examples that do not show up in the training set. What does it mean? That means that, okay, we expect that a good learning algorithm can give you very accurate prediction for those test examples which are looks similar or close to the training examples. But if there are some kind of uncommon examples which are never show up in the training set, right? When it appears, your classifier fails, right? And it's an acceptable result. It's not something you should be mad about. It's possible. I suppose like you're training to recognize human faces, right? And you have like 1 billion human faces, you are doing well in predicting human faces, but right now I give you a new examples. It's some kind of aliens, right? You've never seen the faces of aliens. You fail to do that. It's reasonable. Don't feel mad about that. Does it make sense? Right. So, and sometimes the situation is even worse. Right? We even cannot expect to learn a close approximation to the target function. This is possible as well. the reason may come from the training set. Why? Because when your training set is not sufficient, or your training set have very bad quality. Even your classifier is very strong, you cannot expect your classifier to perform very good. Why? Because machine learning essentially is a data-driven approach, right? It's determined by data quality. That means that means garbage in, garbage out, right?
Is the distribution the same as the target function? Or what's the distinction there?
The distribution.
Is it the same as the target function? You say there's like a mechanism that makes, like the area mechanism that like assigns labels to data, and isn't that the same thing the target function does?
No, the target function determines the function. The input, once the input is determined, the output is fixed. But the issue is that the distribution of the input can vary, right? The chance you look at input 1 is different from the chance you're able to look at input 2. Yeah. So there is a kind of difference here. But the function, I mean, the ground truth function are always assumed to be fixed, a constant. Any other question?
Would we say, I'm having trouble with the same distinction, would we say that the target function generates the distribution?
No. The distribution are about the input instances.
Oh, they're the input.
The inputs, right? But suppose I give you a particular picture, right? I give you a particular picture. I know very sure this picture contains a cat or not, right? This is kind of deterministic predicting procedures. There's no randomness here. But which picture is going to show you is random. Namely, how those pictures are generated and produced are random. They follow some distribution. So in a nutshell, the inputs, the input instances are generated randomly. But once you got one sample of your input instance, then the label is determined, right? Mm-hmm.
So, like, if you have a sample of pictures, all pictures everywhere on the internet, the distribution is like you grab a thing and a certain number of them are cats, and the function is given a specific picture, determine whether it's a cat or not.
Yeah.
Okay.
So don't confuse that here. Like let us model it as a statistic problem, right? So x are random variables, right? X are random variables, but f is a function. F is determined. There is no randomness in f, but fx will be random variable as well. Why? Because a function of random variable is another random variable. So I guess that might confuse you a bit. But f itself is not random at all.
So when you say distribution, you're talking about distribution of x, not the distribution of f of x.
No.
Oh, you are talking about the distribution of f of x?
No, I'm not talking about distribution of fx. I mean, there are some distribution of fx because x are random, right? Then when you apply some kind of function over a random variable, you end up with another random variable. So that means f of x has some distribution as well, right? But this is something we do not care. Okay. Any other question? Okay. So as we mentioned, right? So the performance of your learned hypothesis is also dependent on the quality of the training data. If your training data is very bad, right, you happen to select a bunch of garbage training set, right, you cannot expect your learned hypothesis to perform well. But if the samples you collected are very good, are very representative of the entire training instance space, and then we expect that your learned hypothesis H can perform well, can generalize well on the future instances. So that's something we should be. That's a very important point, right? When we want to characterize the performance of your learning algorithm, because the performance is determined not only the mechanism inside your learning algorithm, but also the input of the learning algorithm, which are the training set. So when we claim whether a specific learning algorithm is doing well or not, can we say, okay, my decision tree or my own deep learner always gives you like 95% accuracy? Can we say? Can we make such kind of argument or a claim?
No, you can't.
Why?
Because we can't pinpoint true error. So we're basing off training error, which is contextual, it's discrete. So we can't say in all cases. At least I assume so.
Yeah. To put it more explicit, as we just mentioned, right? The performance of your classifier not only depends on how smart your learning algorithm is, it also depends on the training data, right? If your training data are garbage, no matter how smart your learning algorithm is, it can perform better. So that means we cannot claim that, okay, on all kinds of situations, I can give you 95% accuracy. No one can do that. And then how can we characterize the performance for a specific machine learning algorithm or model?
It could be true, we just can't say it, right? Like, there is a function f and all that stuff, and there is a distribution. So like, it could be true, we just can't claim it. Is that right?
Yeah, of course. There's function. When claimed, okay, there is a function such that its true error is always less than 0.03, right? But here we're talking about like specific learning algorithm. So remember, the learning algorithm is just a selection procedure, right? So given different set of training data, it will end up producing different hypotheses. Right? And this procedure is determined by two things, right? First, what are the input training data are, and second, what is the search procedure itself. Right? So both aspects can affect the quality of your produced hypothesis. That means when we evaluate the performance of one specific learner, I can now say, okay, I always give you a 100% accurate classifier. That's not reliable because I do not know how well my training data will be, right? Does it make sense? Right? So that's why when we characterize the performance of a learning algorithm, rather than specific hypothesis, because the output of learning algorithm is uncertain. It's dependent on the training set, right? So we cannot say, okay, it always gives you a very good performance, always gives you bad performance. And a realistic definition or claim about your learner is that, okay, with some high probability, my learning algorithm will learn a close approximation to the target function. So see the idea here, right? Because the uncertainty about the quality of your training data, you cannot make a deterministic claim about the generalization performance of your machine learning model, right? What you do is you can only make a probabilistic claim. If I can claim that, okay, with very high probability, like 90% chance, my decision tree can give you a hypothesis with at least 90% accuracy, then we would say, okay, your decision tree learning algorithm is really good. It's much better than mine, or than the orange value theory. But it's not valid to say, okay, no matter what kind of solutions I have, no matter what kind of training data I have, I can always generate hypotheses which give you like 90% accuracy. It's not possible. So see the philosophy here. That's why, like in computational learning theory, all the claims you say is kind of very lengthy and tedious. You say, okay, with some high probability, at least 1 minus delta, your approximation, your learned hypothesis will reach a true error at least 1 minus epsilon. This looks tedious, but we have to be tedious about that because all the claims are probabilistic claim rather than deterministic claim. The reason is due to the uncertainty from the training set, right? This time you have a bunch of very good training set, but next time you may end up with very bad training set. A third time might be like some kind of mixed in between. So that's the realistic expectation about our learned classifier or predictor, whatever, right? So that is when we have a machine learning classifier or model, we say it's good if with high chance, with high probability, our model will learn a close approximation to a target concept. So hopefully you can will this kind of claim as kind of natural things. Don't feel weird about that, because the word is filled of the uncertainty. You cannot make a deterministic claim. So now, that's how we define probably approximately correct concept. That's why it's called tag learning, because it's not deterministic correct learning. So how can we translate this kind of definition in terms of a mathematical language, which is rigorous, right? So we need to introduce small parameters epsilon and delta. So basically epsilon and delta represents the level of the confidence, means how high the probability is that your learning algorithm now is high performance, right? And delta, and epsilon means, this is about delta. Epsilon means that how close your learned hypothesis to the target function. And then use a math language to say this. It's basically like my classifier or my machine learning algorithm with probability at least 1 minus delta produces a hypothesis with error, true error, at most epsilon. And you can set up like epsilon to be 0.1 and delta to be 1. It means that, okay, with probability at least 90%, my own machine learning learner can produce a hypothesis with true error at most 0.1. Of course, the smaller epsilon, the smaller delta, the better your performance, the performance of your model, right? Is everybody comfortable? And then we'll, based on this definition, we'll say a few kind of conclusions, right? We'll say how can we estimate or how can we make epsilon delta in terms of the empirical error, namely training error. And this kind of proof and inference is based on our assumption that the distribution on the training set and test set are the same. So we'll see it clearly when we look at some concrete example later. Okay, I think let's stop here today. Right? So hopefully those concepts can give you some sense like how, in theory, can we measure or characterize the performance of machine learning model. This kind of like counterintuitive, but when you get used to that, you say, okay, it's very natural. Okay.
Like, I was homework 0 after the day.